Welcome. This is the first A2 Astrophysics. This is the optional unit, okay, for A2 AQA Physics, okay. Now, I'm not doing the other ones, such as turning points in physics and medical physics, purely because, well, I'm not doing them, so I'm not going to produce a video on them. So I'm sorry about that, but just the way it is. I might do it in the summer for next year, but obviously it'd be pointless for you watching this video this year. Anyway, you probably wouldn't be watching this if you... Oh, shut up. Okay, so anyway, in this video, there's going to be three of these astrophysics ones, and quite clearly this one is the first, okay? And they kind of... Sorry, one sec, let me... let's get the plan. Okay, so it's all about optical and non-optical telescopes. Okay, so just going to be giving a bit of a recap of lenses. Okay, something you should remember from GCSE. Okay, and then obviously we're going to be building on that, adding a few more things to it. We're going to be looking at telescopes. Okay, reflecting telescopes. And as well as all that, we'll be doing a few of the things just mentioning as we go through. Okay, so let's kick off. So the first one that I want to talk about is this the convex and concave. Now, as I said, it's a GCSE thing really, so it should only take a few moments. Okay, so obviously, this is what a that's a convex lens. Okay, and the one on the bottom will be a concave. Okay, I've drawn it, and they obviously have very, very different effects. Now, you should also know you might see convex lenses also referred to as a converging and converging lens, and concave as a diverging lens. And obviously that's related to what happens when the light rays go through. Okay, now this is a very basic example of light rays going through. We're going to look at exactly what happens to these light rays when they go through a bit later on. Okay, we look at something called chromatic and spherical aberrations. Okay, but for the moment we're assuming there is none of that in these very high quality lenses. Okay, so anyway, the light rays go in there, but what happens next for each of them is very different. Okay, so on the convex stuff, as I said, the converging, so they come together at something called the focal points, which you'll see that didn't work out, but you get the idea. Okay, and that is called that point where they meet on the principal axis, which is this horizontal line. Okay, that's the principal axis, but this is the principal focus, which is where they focus on, obviously. And the length between the principal focus and the lens is obviously called the focal length, which is key. As I said, in this video for the A2 stuff, we're going to be looking at the convex a lot more than the concave, and purely because all the concave does is just spread the light out. Okay, just does the opposite effects really to the convex lens. So as I said, as I said anyway, they're the two types of lenses. Okay, so hopefully you're familiar, or should be anyway, with both of them lenses. Okay, but really, as I said, that's something you probably covered way back in GCSE, and depending on obviously what you did at GCSE, you might have looked at different focal. What we're going to do now, as I said, is something you might have done GCSE, where we look at putting in object on the left hand side of the convex lens, okay, and looking at what effect that has in terms of is the image real, inverted, magnified, diminished, etc., etc. Okay, so we're going to focus on another example of a convex lens. Okay, so we're not going to be, so remember this is the principal axis. Okay, so we've got our standard light rays. These obviously haven't. Oh no, sorry. So, actually, we've focused on that. So this I'm going to label here as F. Okay, and that's the focal point or the principal focus. Where if we just had standard light rays coming in, they would all focus on that point. Okay, but what we do here is we look at putting the object at varying focal lengths and seeing where the image comes up. Now, the obvious one to do is put it at less than one focal length. Now, obviously, if we put it on this side of the lens, the object, you'd be looking at it through this way. Okay, so it's logical to put the object on the left-hand side of the lens. So, as I said, you need to be kind of specific, or you can just remember what happens. Okay, so I don't know. Let's just put it less than one focal length. So, sort of about there. Okay, so object, I'll move away in a minute. So sort of is less than one focal length. Okay, so you could come up with your own focal length, but it's just key that for the first little bit of it, you put it less than one focal length. And what we do is obviously we draw a line directly from the object, a light ray, to the lens. Okay, and what happens is one of these light rays goes through the centre of the lens. Okay, and the other one goes through the principal focus. Okay, and you can quite clearly see that these two lines, if you carried them on and on, they would never meet. Okay, because they are converging, because that's the idea. Okay, so what your eye does. So if we put an observer, to excuse my art skills, there. Okay, just some weird ass eyebrows. Anyway, so what the eye would do is your brain would track these lines back. Okay, that would be coming into the focus. Right, isn't it? Oh, sorry. Coming from the right place. So one would be coming from the object itself, and the other would be coming from where the light rays went in. Okay, and obviously where them two met. Okay, that would be where your image is. Okay, so less than one focal length, that's what your drawing would look like. But there's a couple of things that we need to know on here as well before I start talking about what this all represents. Okay, so the distance between the focal length, between the focus point and the convex lens, okay, that is known as little v, okay, and a distance, oh sorry, no, it's not v, at all. I do apologise. Shut up. It's known as little f. I do apologise. Okay, and the distance to the object from the lens, that is known as little u. Okay, and it's positive if u is on the left hand side. Okay, v on the other hand is the distance from the image, sorry, from the lens to the image, and it is positive if it is going on to the right. But obviously, if it's on the left hand side, it's negative. So, but we still leave it as v. Okay. All right. So that's just a few little notes that you need to make. Okay, about what the distances represent. Okay, well these, because obviously we're going to come up with a few formulas. Like the first one you should be familiar with is 1 over u plus 1 over v is equal to 1 over f. F being the focal length, u and v being the length that I described. The u being the distance from the convex lens to the object, and the positive version of that being on the left hand side of the lens, and obviously the v is the distance from the convex lens to the image. But there's a couple of things that we can say about this image. Okay, well, there's 3 questions, and it applies when we vary the focal length. So we ask ourselves these questions, and the questions aren't such that, why the hell are we doing physics? Why are we wasting our life doing this, a GCSE crap? Well, it's just always nice to get a bit of a refresh. Anyway, apart from that, the 3 questions that you ask yourself are: is the image real or is it virtual? Okay, and if it's real, then it's on the opposite side of the lens to the object, and therefore, obviously by power reduction. If it's on the same side as the object, this is the image. If the image is on the same side as the object, then it is virtual, or quite clearly that is virtual. Okay, so I'll make a note of these questions actually on the top. So I'll put R or big V, real or virtual. And then the next one is magnified or diminished. We can tell this, and I'll go into more in his actual calculation of this later on, but for the moment you can just look at the height of the object arrow, okay, which is this thing here up to the red line, and the height of the image arrow, which is up to obviously the dotted line, or it would be the red line if the image is on the right hand side for the lens. Okay, so therefore quite clearly this one is magnified. Okay, the third question we ask ourselves, well, is it upright or inverted? Well, if it's upright, it's pointing, so if above, if they are both above if the image arrow is on the same, if they're both above the principal axis, then it's upright. If the object is pointing above the principal axis, but the image is pointing below, then we say it's inverted. Okay, so hopefully that makes sense. So is it upright or inverted? Okay, so quite clearly that is upright. Okay, but as I said, I'll be putting a table on at the end of this, towards the end of this, which kind of brings all the focal lengths together. So you don't need to note down so much about the virtual, magnified and upright for less than one focal length, but I'll be putting it on a table, so you don't have to write that all down just yet. Okay, so if we take this in a slightly different way, okay, so obviously I'm going to keep the same lens, if I can, obviously. Might not be able to, but you never know. Okay, a sec, sorry. Keep the focal length the same. Okay, so this time what we're going to do is between 1 and 2 focal lengths. So you can just sort of measure it out, okay, and I'll have a kind of good enough go at this, I reckon. So if we put it somewhere about there, okay, and this is obviously going to be the object, and as before we have a light ray coming from obviously the same height as the object, arrow up to the top of the lens, okay, and obviously that's going to go through the focal point. Okay, but also it needs to go directly through the centre of the lens, and obviously where they intersect is where the image is going to be. Okay, now I've drawn this arrow right to the top. Okay, I could have drawn it in exactly the same height as I did for the first focal length, and the effect of whether the object was magnified or, sorry, the image was magnified or diminished will be exactly the same because of the way the arrows end up being refracted. Okay, anyway, so hopefully that explains. I'm not just said it's magnified because I've drawn a bigger arrow. Okay, so anyway, quite clearly, therefore, this is the image arrow. So the image is there, and we ask ourselves exactly the same question. Is it real or virtual? Well, as I said, it's quite clearly real image because it's on the opposite side to the object, okay, the lens. Is it magnified or diminished? Well, quite clearly it is diminished because the arrow is smaller, okay. Oh, maybe that's just my cruddy drawing. I think that's just my crud drawing. Do apologise. Yeah, it should be magnified, sorry. Sorry, I do apologise. I don't think I've drawn this quite out. Let me measure it out. There you go. Yeah, I think it's just my cruddy drawing. Yeah, it should be magnified anyway. Okay, so it should be magnified. I've just not drawn it as such. Alright, it's obviously inverted and it is real. Okay, so I do apologise. Even it should be magnified if it's between 1 and 2 focal lengths. So my drawing's just not come out very well, quite clearly. Okay, so the next one that we're going to look at is obviously going to be greater than 2 focal lengths. Okay, so it's the same principle. So if you compare the focal lengths, sorry, my drawing's gone a bit crud now, but whatever. You can do the object somewhere over here. And as before, we're going to have a light ray coming from the object to hitting the convex lens. Okay, and as before, one's going to go through the centre. Okay. And we have our image. Okay, so as I said, you want to measure these, but really what happens, is it real or virtual? Well, obviously it's real because it's on a different side to the object. Okay, so the image is on a different side to the object, so therefore it's real, and they're all real apart from sorry, that's meant to be at 2 focal lengths, by the way. Is it? One second, just measure. What was it? 2. Oh, it's great. It's not quite 2, but it, yeah, it's not gone perfect. Yeah. Anyway, at 2 focal lengths, the object and the image are exactly the same size. Maybe that's not a perfect example, but I think it's close enough anyway. Okay. So anyway. It's real because it's on the opposite side. It's not magnified or diminished. It remains the same size at 2 focal lengths. And if it's upright or inverted, well, quite clearly, as all the others are, apart from less than 1 focal length, it is it is inverted. Okay. So let's do now. We've done less than 1 focal length, between 1 and 2, and that was meant to be directly at 2. Okay. Let's see what happens when we do it greater than 2 focal lengths. I'm not going to move the object, I'm just going to move the focal point of the lens. Okay. Essentially you could think of it as the same, but obviously I just don't have enough room to move the object a bit further back, so I'm cheating really. Okay, so anyway, if we drew the lines through the focal length, see where they meet. Okay. Well, quite clearly you can see there the image is a lot smaller. Okay. So it's quite clearly diminished for greater than 2 focal lengths. It's real and it's inverted. Okay, so let's put all that information. I've gone through that fairly quickly and maybe not so well. Let's put all this information in a little bit of a table. Okay, so the first column that you might want to put is the focal lengths. Oh, sorry, one sec. Actually, let me just put my lengths on here. So, V. Okay, so you want to put a length of your focal lengths. Sorry, a table with the first column of the focal lengths. The second column, you want to put, well, is it real or virtual? So R or V. Okay. And your third column, you put M or D, so magnified or diminished. And your fourth and final column is upright or inverted. Okay, so U or I. Okay, so we're just going to fill in that table now with bits of information that you should be aware of. Okay, so anyway, between less than 1 focal length, okay, so less than 1, we said it was virtual. Okay, we said, well, was it magnified or diminished? Well, we said it was magnified, and if it was upright or inverted, well, it was upright. Okay, so less than 1 focal length, it was a virtual image, it was magnified, and it was upright. Between 1 and 2 focal lengths, we said it was a real. We said that it was magnified. and we said that it was inverted. And then at 2 focal lengths, we said the image was still real, okay, but this time it wasn't magnified or diminished, so I put like a little arrow pointing both ways, and also it was inverted, okay. And then greater than 2 focal lengths, okay, well we said it was still real, but it was diminished and it was inverted, okay. So that's just a table. If you want to learn that table, you can do. Obviously, you know, you can learn anything if you want to, but as I said, if you don't remember that, and you're better at drawing lenses than quite clearly I am, but obviously that's because I've not got a proper, you know, ruler there, and I can list a few excuses for you, but I don't think any of them would probably be good enough. But yeah, anyway, so as I said, they're just a couple of focal lengths that you might want to consider. Okay, so as I said, that was more of a refresh. But what we need to do now is take this up a little bit of a notch. Now I said well, we magnify because the arrow was bigger, but specifically, what can we take away from this table? Okay, I put this table on for a reason here. To the looking at the component that says, well, is it magnified or is it diminished? Okay. Well, if you look at the table, what focal length has a magnified, what focal length produced a magnified image or a diminished image? Well, if we go from the furthest away, okay, so greater than 2 focal lengths, well, it was diminished, and then at 2, it remained the same size. And basically, the closer we got to being a smaller focal length, the more magnified it was. Now, maybe that's not true right up until the very, you know, first point, the very smallest focal length. But you get the idea that the closer it is, generally, the more magnified it will be. So, what does that mean? Okay, so I said the object is closer to the focal, to the lens. Okay, what does this actually mean? Well, it's a ratio of the distance, okay, between the object and the lens, and the distance between the image and the lens, okay. So what essentially we said was if the distance between the object and the lens is less, then the magnification will be greater because it will produce a okay, hopefully that makes some kind of sense. And obviously the distance between the image and the lens also has to be considered, okay. So basically the magnification is greater if the distance from the object to the lens is less, or the distance from the image to the lens is greater, okay. So what we come up with here is a magnification formula which says V over U, which just, so obviously quite clearly that explains what I've just said. The magnification will be greater if the distance to the image is greater, or the distance to the object is less. This is from the lens, okay, which is obviously highlighted by that formula. So hopefully I've explained it there. But just to recap, if you didn't know what we mean by focal lengths, okay, well this focal point, obviously, if V was F, in other words, if the image produced was at the focal point, which it probably would be very unlikely to be there, then we can say V equals F. But if that confuses you, don't worry. What I'm trying to say is we look at U, so the distance of the object to the lens, okay, we look at it in terms of, what's that in terms of the ratio of the distance from the lens to the principal focus, okay? So the principal, so this little f, the distance between the little f and the lens, we call that the principal focus, okay? And obviously that's got a focal length of 1 because it's a focal length. And we look at that distance, whatever distance that might be, obviously it's different for different lenses, and we look at that as, well, how many of them could we put into the distance between the object and the lens, okay? If we can put 2 of them, so if the distance between the object and the lens is twice the length of the distance between the focal point and the lens, okay, then we call it 2 focal lengths. and if it's the same distance, then we call it 1 focal length. If it's u is 3 lots of the focal length, then we call it 3 focal lengths. Okay, so if u is 3 times as big as the focal length, then it's 3 focal lengths. Okay, hopefully that makes some kind of sense. That's what we mean by focal lengths, but maybe I kind of assumed that I may have said that already, but it doesn't really matter. Okay, so that's the introduction, really, to at the astrophysics topic. Okay, so what we're going to look at now is something, just making sure I've not missed anything out. Do apologise. There we are. Sorry. Yeah. So what I'm going to look at now is something called normal adjustment. Now the main uses of lenses, obviously after glasses and typical stuff like that, is, well, obviously, you know, for sciencey people, which obviously hopefully we are, one of the main uses is obviously in telescopes. Okay, I'll remove that weird looking eye off the board there. Okay, so obviously telescopes are a great user of lenses. Okay. Sorry, let me just. And in telescopes, they use something called normal adjustment. Which, what the hell do we mean by normal adjustment? Well, I'm going to draw a sort of an example of it on the board in a minute. But essentially, what it does is it magnifies something that's far away and make it look like it's quite close. In other words, it magnifies it. Okay. And that's essentially what it was, what we were looking at then. But what, as I said, if you look online if you type in obviously online, normal adjustment, you will come up with many varying different diagrams. Okay, and many of these diagrams will, all of them have in common 2 convex lenses. Okay, which look like this. Is that fair? Okay, and some of them, well, I say most of them, will have the light, which is obviously coming from the left of the lenses. Okay, sorry, I've not drawn my lenses far enough along the axis there. Sorry, a sec. They will have the light coming from a certain angle. Okay, and all that means, I'm going to draw the light coming from a parallel, so a level a plane, so they're all parallel to each other, and that's because they're parallel if they're coming from a very far distance away. Some of them draw them you know, at an angle because that's the way the lights come in, but the fact that these lines are parallel suggests they're coming from far away, which is the lenses that I was using before. Okay, and I was highlighting convex and concave. Now, quite clearly, you know, when we were talking about lights way back in Unit 1, okay, we said obviously they're packets of electromagnetic waves, which look something like that. Okay, so I can't do a very good example, but you get the idea. Okay, and obviously they're made of photons, which are quite clearly not going to be level. Okay, because obviously they're affected by the electromagnetic spectrum. Anyway, okay, so what am I trying to say here? Well, normal adjustment really is just about making something bigger. So it's putting these back to front, but if we just put one lens in the telescope, well, it wouldn't be very powerful for a kickoff, but it put it on a focal point, like what we've been talking about just a few minutes ago. Well, actually, a good few 10 minutes ago or whatever. But it'd be focusing on a point, and it's very hard to, you know, you'd have to be exactly at that point to see the magnified image. Okay, so what they do instead is put 2 convex lenses back to front. Okay, so you've got one focusing on the other way. Okay, well, not back to front, together really is a better word. So that it's magnified, but then the other lens brings it back up so you can see it, and that becomes a lot more apparent when we draw a diagram of that. Okay, so actually what I'm going to do now is just pause the video, have a drawn diagram, and then I can go through it with you actually. So anyway, sorry, this next bit is normal adjustment here. Okay, so I've kind of drawn a little bit of a graph here for you. Okay, so the red light rays are indicating light entering the normal adjustment system, if you can call it that, and hitting the principal focus, okay? Now, what I've labelled here is FO, and that's not a coded message. Although you might want it to be. It's just the focal length of the objective lens, which is the first convex lens the light hits, okay? And Fe is not iron, okay, unfortunately, for those chemistry plebs. It's the focal length of the eyepiece lens. Now I said it's used in telescopes, obviously, to make, magnify things, okay? So that's obviously, weirdly enough, where your eye would go. Okay, so anyway, it comes out parallel as well. Alright, so I put a few equations on here. Now, this normal adjustment one, D is equal to FO plus FE. Obviously, just that's the total distance between the objective lens and the eyepiece lens. Now, the magnification, just like when we were looking at the standard single convex lens, we were looking at a ratio of the the length between the image and the convex lens and the convex lens and the object. Okay, similar kind of thing here, but obviously we're not looking at an image and an object. We're just looking at the ratio of the two focal lengths. Obviously, because a greater magnification would require a greater focal length. So whichever because they're both convex lenses. One's just called the objective lens, which is obviously what the light hits first, and one's called the eyepiece lens. But they both are convex lenses, so whichever has the greatest focal length has the greatest magnification. Okay, and it's just the overall magnification is just a ratio of the two. Okay. So obviously, if because obviously if the lens which is entering, the light is entering first, if that's got a greater magnification, then you can think of it, it's almost like, you get around your head of it, it's almost like being distorted. If you're boosting it straight away, it's better than boosting a poor signal, if that makes sense. Obviously, that's not relevant to this, but it just tries to help you get your head around it, okay? But as I said, I'm fairly sure these two are given in your formula sheet anyway, so as I said, no real worries on that. But I've just drawn them horizontal, because that's the way I've drawn them. If that's wrong, I'm fairly sure it's not, but I only say if it's wrong, because most of the examples that you will see online are coming at some kind of angle, but that's completely fine as well. And obviously, when they come in at that angle, they come out of the eyepiece lens at a different angle, and it's a ratio of the two. Now, maybe you can talk complete and utter crap, and that's totally okay, because I'm not being paid to do this, so I can do whatever I want. Apart from, murder a couple of people in front of the camera. That's probably pretty bad. But anyway, as I said, you're given them equations, and it's easier just to learn the horizontal drawing as well, okay? Now, if you look online, I think June 2010, the question 1, something on there has got a question of drawing that, and that is completely acceptable. They don't say it has to be at an angle. They don't say it has to be horizontal either, for that matter. They just have obviously a few requirements. It's got to be parallel. The lines have got to be parallel coming in and parallel leaving. Okay, which they are. So there's absolutely nothing wrong with that at all. Okay, so that's normal adjustment, and obviously you may be asked in a question, it's quite likely you'll be asked to manipulate these two equations, okay, in terms of, you might be told the magnification of one of the focal lengths, okay, and it's just a case of subbing in the two equations, almost like simultaneous equations, okay, but as I said, that's all you probably will be asked on normal adjustment, okay, so nothing too challenging on that, okay, right. Sorry. There's the booklet. I do apologise, I've put it over there. 9.1 up. Dear. Right, there. I do apologise. Okay, so hopefully said that normal adjustment kind of made a little bit of sense. Now what we're going to go back to is, I was debating whether to do this actually when I first started mentioning convex and concave lenses right at the start of the video, but for reasons because, well, I'd already set it up in this method, and you know, it would have taken a bit of effort to write it down and readjust it and whatever. I just thought I'd fit it in at this point. Now, there's two types. There's the next thing we're going to talk about is spherical aberrations and chromatic aberrations. Now, I'm going to start with chromatic because it sounds easier. Well, it doesn't sound more complicated, but it's more relatable to something you've done last year. Now, the word chromatic, okay, is whenever you hear, well, what does chromatic mean? Okay, well, one sec, chromatic aberration. Okay, chromatic aberration, well, obviously anything that is chromatic is to do with light, okay? So, as I said, the word that you would more likely to associate this and see it straight away is monochromatic, which means light of a single wavelength, which is what you would have used in Young's double slits, okay? So that's a bit of a recap to AS, but you're probably not really doing that. Anyway, so that's why we, obviously monochromatics, therefore you can obviously dictate what chromatic means. It's the aberration to do with wavelength. But obviously to understand all of that we know what chromatic means. What the hell does aberration mean? Well, aberration is just essentially, it's just another fancy word for saying a fault with something. So therefore, by power of insane, clever logic, putting them two together, wavelength, fault. It's a fault to do with the wavelength, but still doesn't really answer our question. It's like kind of, you know, speaking in French, you can convert the words, but does it actually make any sense? In my day, in my French, the good old days, it never did. I just said French words and hoped it made some kind of sense. So yeah, that's my qualifications. Anyway, so what we're talking about here is faults with wavelengths, okay? And if we relate that, as we have to, with a convex lens, well, I'm just going to draw a convex lens out. So we'll have the standard wavelengths going in. Actually, I'm going to need a different colour. Craziness. How well prepared I am. So this light's going to be green now, and I'm going to do that because I can. Okay, so we've got these light rays entering. Now, it's a fault to do with the wavelength, okay? Well, a convex lens assumes the wavelengths stay the same before and after. The light isn't split up, okay, into different wavelengths, hence a fault with the wavelengths. So I've probably given too much away already, but it's still going to hit the focal point, but only some wavelengths of light are going to hit that focal point. Okay, so we call this focal point F. I probably shouldn't have done it in blue, to be honest. Not going to change that. Okay, so we call this obviously the focal point there. Now, some light is going to hit that, but what colour light is very dependent. Okay, so we might have, it's basically each line is split up into red and blue light. Okay. Now, I've probably drawn too many light rays, but you get the idea. Okay, so I'm going to do it for everyone. But some are going to hit it, some aren't. Okay. So you get the idea. Each light ray is now going to be split up into various. Instead of the convex lens splitting it up into one, it's just simply refracting it. It's now also splitting it up because obviously, as we know, white light is obviously made up of a vastly different amount of wavelengths and colours. And what chromatic aberration does, it's to do with the actual convex lens in terms of, is it very high quality or not? If it's not very high quality, then it suffers from chromatic aberration, which splits up the light because of some imperfections in the glass. Maybe the molecules interact. The structure is not pure glass. Maybe it's got a bit of some other materials in there which have a different refractive index, okay, which cause the splitting up of the light ray. So that's essentially why it splits up. Hopefully, so you don't need to know that, and probably doesn't make that much sense, but essentially that's what chromatic aberration is. So it's to do with the splitting of the wavelengths, okay, to do with light. Now obviously you generally won't be shining anything other than white light, but any other wavelengths can still be broken up into different colours. I just used white as an example because it's probably the most common and the ones I'm going to ask you on, which is split up to red and blue. Anyway, so that's what chromatic aberration is. So what we're going to look at now is spherical aberration. Now using the same principle, well, aberration, same word, weirdly enough, so it still means the same thing. Crazy. So it's still a fault, but what the hell does spherical mean? Well, obviously it doesn't have any different meaning to what you know it from before. Maybe that, what the hell does that mean? Maybe sound a bit dumb, but at the end of the day I don't really care. So spherical aberration, well, spherical is obviously to do with some kind of circular shape. Aberration is to do with fault, so it's to do with the fault of a shape, okay? And obviously any aberrations that we talk about in this kind of instance, well, there's only two, obviously. Obvious, you should have known that's why you're watching this video, of course. Stupid. Okay, so what I'm trying to say is all of this will be to do with convex lenses. The faults. Now, it's a fault to do with the shape of a convex lens. Now, what the hell do we mean by that? Well, if you look at the shape of this rather crappy drawing here, the principle remains the same. I mean, it looks like I'm going to say it. What I'm trying to get across is there's different distances. So at the centre, going if you went through just above or below the principal axis, which is say the horizontal line, there's quite a big distance for the light to go through. And towards the top, there's a much smaller distance. Now, obviously, the more of the material there is, the more it's going to be refracted, maybe more than once. But in its essence, the light ray that's going in isn't any different, to the top or at the bottom or at the middle of this convex lens. It's the distance it has to travel, which obviously means it's going to be refracted by different amounts. So essentially what happens is that obviously the light ray comes in as per normal, but instead of being all perfectly refracted onto the focal point, some is refracted by a greater amount, some is not by as great an amount. Now obviously it will be reflected by a greater amount at closer to the centre of the more thicker part of the lens, but I've just kind of screwed that up, but it doesn't really matter because I don't care, it's not an exam. Okay, so that's what spherical aberration means. So the key difference between the two, they're both to do with faults of the lens, and obviously they're both to do with quality, and you can both improve them with the actual quality of the lens. But because these lenses are going to be so big that we deal with, because obviously convex lenses are mainly used in telescopes, they're going to be so big that it's going to be very hard not to have a little bit of either spherical or chromatic aberration. Okay, but we just assume generally that there isn't, which is quite negligible. Okay, but anyway, that's our advantages and disadvantages. We'll get on to later on. Okay, but as I said, spherical aberration is to do with the shape. Obviously, faults to do with the shape, causing the light rays to be refracted by different amounts because they travel different distances because it's not a perfectly rectangular shape, which obviously a lens isn't. Okay. And chromatic aberration is to do with light faults in terms of the light split up by the material of the convex lens. Okay. Right. So they're kind of the two. It's kind of more knowledge based, well, as opposed to the rest of it, which obviously isn't. Okay. But really, hopefully, I've kind of broke that down into a bit more manageable stuff. So what we've looked at so far is refracting, lenses, and obviously they're pointed telescopes, which we looked in normal adjustment, and we said obviously, they're quite clearly refracting telescopes. So what we're going to look at now is obviously the opposite end of the scale, and well, not so much, reflecting telescopes. Now, obviously you know what reflecting means. It's like a mirror. The light bounces back. Okay, so it's a similar kind of thing in this instance, but in essence, the actual diagram is quite vastly different. Okay, so just going to do a quick sketch now. There's a high-tech rubber there. Again, don't really care. So it looks. There's two types, by the way. There's one called the Newtonian telescope, which is very nice. There's nothing wrong with it. And you hear the word Newtonian, you think that's pretty good. But essentially, the second type of telescope, the Cassegrain one, is more commonly used because you can attach, because with the shape of it, you can attach more heavy, complex equipment to measure it and measure the light rays to see where the light has come from. Obviously, telescopes measure planets and stuff far away. Okay, so you know, it allows, if they can fit more complex heavy equipment to the base of the second telescope we're going to look at, the Casagreen one, obviously that allows them to analyse it, you know, greater detail. Anyway, so we need to actually draw the telescopes first. Okay, so this first one, as I said, they look basically the same. So what we've got is sort of half a convex lens, sorry, concave lens, but it's on this concave lens. We call it the primary mirror, by the way, and that will become obvious why in a few minutes. The primary mirror. Okay, and it's filled. It's kind of backing. Okay, so on the curvature part of it, it's filled with a very thin layer. I think 25 nanometers, which is a very small amount. Okay, very thin layer of aluminium atoms to help it bounce back and reduce the chance of chromatic or spherical aberration, obviously, because it's not going to be perfectly curved. Okay, there's a chance for it to be not. Anyway, so what we have here is we have this primary mirror, okay, and we also have about halfway, you know, towards the end, okay, we've got this slanted mirror, okay, which we call the secondary mirror. And what we draw now is the light rays, okay, so yeah. So obviously we've got light rays coming at the bottom and the top of the mirror. Can't have it coming through the primary, sorry, we can't have it coming through the secondary. Okay, so line there. Obviously they're entering, okay, obviously they bounce back. We have two lines at the top and two lines light rays at the bottom. Obviously you would have a lot more, but this is just simply for show. Okay, and obviously all of them light rays bounce back to hit the secondary mirror. I'll move out of the way in a second. Okay, and then they hit the secondary mirror, but where do they go then? Well, obviously they're all reflected directly down. Okay, to this electronic camera, which essentially it's not, you know, the standard camera that I'm recording this with. It's a bit out, probably out of its depth. If I were to try that, essentially what happens is in this electronic camera, it analyses, obviously looks at the angles that it's come in from. And obviously uses intelligent, sophisticated methods to work out how old is this light, so how far has it travelled, you know, stuff like that. Okay, so that's essentially the first type of telescope. That's called a Newtonian telescope. And the reason why you can't attach heavy stuff to that is because, well, it's all focused on this camera, okay, so you need stuff to support the secondary, and the heaviest bit is quite clearly the primary mirror, because if you've not held it before, glass is quite heavy, and this is what this primary mirror is mainly made of, okay, so that's the heavy base, and it's just the light's reflected off the heavy base, and the main body of where the analytics is taking place is this rather lightly suspended camera, okay, obviously electronic camera, but still you can only monitor so much. Now the second sort of telescope, and the one that's more commonly used, is something called the Casagreen telescope. Now essentially this is exactly the same as the Newtonian telescope, however the primary mirror is split up here into two halves of this sort of concave mirror, but okay, so it's still a mirror, and the camera is essentially moved to the back, okay, so essentially these light rays bounce, and then the mirror is now, second mirror is now vertical, okay, bounces straight back and goes through the gap in the primary mirror to the electronic camera, okay. Essentially that's what I'm going to draw. So actually I'll just give the video a pause so you'd have to keep watching the back of my head and it'll be on there in a second. So what I'm drawing on the board there is what we call the Casagreen telescope, okay. So as you can see, it's pretty much what we're saying. Weirdly enough, that's a bit crazy, but we still got the same principle of the light entering the system, okay. Obviously we assume this to be kind of the base of the telescope. Obviously if we were continuing this on, obviously to the left, over here we'd probably fall over my books and stuff, but it'd be the end of the telescope, okay? So, you know, where the light enters and then it bounces off the back, the very end of the telescope, and hits the mirror and comes back, okay? So, same principle applies for the Newtonian and the Cassegrain, but as you can see, this is now split up and the camera has moved behind it, okay? Now, this is better, as I said, because you can now fit more, because this is essentially the base of the telescope, where the heaviest bit is. You can add more weight to that, essentially, so it's not going to sort of topple over or anything, and it's very easy to put more complex equipment there, obviously, which can, you know, help to measure, get more data. But there's also this thing as well, that the collecting power of the mirrors, of the telescope, so how much detail it can obtain, is directly proportional to the diameter of the primary mirror square. Now, the fact that it's squared might be a bit weird, but hopefully it does make sense that you know, the greater the diameter, the more information or, you know, light can hit the mirror, okay? And obviously, therefore, if there's more light that can hit the mirror, there's more information that can hit the mirror, okay? So obviously more for analysing it in a greater collecting power, which is just, you know, how well it can look at things, if that is the you know, human definition of it. Okay, so anyway, that's essentially the two differences between the two telescopes, okay? And it was quite obvious why I didn't try and doodle all that, because it's a lot of drawing for not a lot of explanation. Okay, so essentially that's the differences between the two, and you just need to know that formula at the bottom there, okay? And obviously the constant proportionality is, you know, you probably will be told that, but that's just something for you to know, okay? So that's kind of it. Now, the main okay, so what we're going to go on to now is the disadvantages of refracting telescopes and the advantages of reflecting telescopes. Now, obviously, the disadvantages, they're basically opposites of each other. So the disadvantages of reflecting telescopes are the advantages of refracting telescopes. And obviously, because we're looking at the disadvantages of refracting and the advantages of reflecting, they are the opposite of each other. So, you know, the big refracting ones with the convex lenses, they're very, very heavy. And as we proved before, when we looked at convex lenses, we led them to believe that they can adhere to spherical aberration, which, as I said, you know, the fact that the light travels a different distance in where it enters the telescope, in the mirror lens, if you want to think of it like that. Excuse me. Obviously, that causes it to be diffracted by different amounts, okay, which means that it's not entirely, you know, error-free kind of thing. And the chromatic aberration, which we said was to do with wavelengths, essentially is to do with light, okay? And obviously, quite clearly, reflecting telescopes don't have that problem, because all of the, it's just simply bounced back, okay? So it's not going to be, it's not diffracted by any different amounts, okay? It bounces, you know, it all goes exactly the same way, okay? The refracting telescopes, because it's one big lens, okay, it's very difficult to move. Where I know this is it looks quite difficult because it's a big heavy primary mirror, but there's also, it's fairly light in contrast to the refracting telescopes. So the reflecting are quite easy to move, okay? And obviously we don't have focal lengths with these because we're not refracting, we're reflecting it, weirdly enough, okay? So we don't need it to be, we don't need the focal length to be great, okay? It just needs to be able to bounce the light back, and that's all we're really bothered about, okay? I mean, obviously the angles and stuff may have to be a problem, but what I'm trying to say here is, obviously, as I was mentioning, if you want a greater magnification, okay, what essentially you have to have is a greater focal length, which means if you have a greater focal length, you need a bigger lens, okay, which means more weight, obviously. And obviously, as I said, this doesn't really apply to it, so you can keep these telescopes kind of small, which is why they're easy to manoeuvre, okay? And obviously, if they're easy to manoeuvre, and essentially they do the same thing as refracting telescopes, Okay, they can obviously respond to, you know, any astronomical events that happen just out of the blue. Okay, so very, very easy to adapt to. So the advantages of these are the disadvantages of refracting. No, okay, can't speak anymore. The other ones. Okay, so hopefully, as I said, it's nothing too difficult, and we've kind of gone on to that there. So that's all for kind of reflecting telescopes. We're just going to look at telescopes kind of in general now. I mean, it's more related to these, okay, than refracting, but the principle stands, okay. So, yeah, I'm just going to do another one of my famous, where I set it up, because there's a few more diagrams that we have to draw, as with astrophysics. It's quite diagrammy, so I'll just be a second and I'll have another go at drawing a few more diagrams. So I've now had a go at drawing all them this next diagrams, okay, and I have obviously changed my shirt. I've you know, obviously new day and all, but still night time anyway. Early morning stuff. Anyway, what this is showing, okay, well, these two dots, the balls and weird away. Okay, these are meant to represent planets, you know, planet A and B, for example, just to you know, make sure you're not being abnormal. Anyway, okay, so basically what this line, this horizontal line here represents, it represents the aperture of the telescope. Okay, so this light coming into the telescope from these two planets, okay, or stars, or whatever they may be. Okay, and they're separated by a distance I've labelled x, and the distance from the star to the telescope I've labelled L. Okay, now these sort of graphs here, okay, they are intensity graphs, which I'm trying to sound intelligent there, but it's not works. Infer that there is interference. Oh, I thought it was going to work then. Anyway, okay, so we've got the varying difference. Obviously, they're all at the same length or distance away from the telescope, but their separation is what changes here. And obviously, it gives rise to these different intensity graphs. Obviously, intensity from the light interfering on the screen of the telescope, okay? And it doesn't really matter what type of telescope is used. It could be, you know, the reflecting or the refracting telescopes, okay? It would both, if you were to look at the electronic camera that captures the intensity, okay, you would get a graph such as these, okay? Now, what you should notice, and I've wrote down here a little bit extra as well for those of you that don't really pay attention to me, just look on the board. We've got that the central maximum is, or peak is also known as an Airy disk. Probably not obvious, but in terms of the way it's written it, but the central maximum, okay, which is where there is constructive interference, it's almost it's twice the width of any other maximum, okay, is also known as the Airy disk, okay. Now, as I said, that doesn't have any other effect, but it's just sometimes in the exam they will refer to it as the Airy disk. So, and it's not a disk that's got air in it, but you get the idea. Okay, so what the hell do we mean by reasonable, critical, and reasonable? I was spelled that wrong. That isn't even right, but you get the idea. Okay, so what do we mean? Well, basically, in essence, in the very, very shorthand definition, okay, which is obviously not scientific, but it's a way to look at it to build up to the scientific stuff, it's, can you tell us two different planets? Now, obviously, we can tell, you know, just by looking at this diagram, there's clearly two planets in every situation. But this is what you'd be looking at. Obviously, you wouldn't be able to see that. If you would be able to see that, you wouldn't need the telescope in the first place. But what these interference graphs says is, yes, there are light sources coming from two different planets, indicating two different planets. And obviously, you can work out the intensity to how far them planets are away from each other, and varying things that we'll go into in a minute. But essentially what it is can you see a difference in the two peaks? Can you see two peaks or can you see one peak? And quite clearly, you can see it for reasonable, you can just about see it in the critical, and the unreasonable, well, it just looks like there's one, and you could say there's two. I've just drawn like one inside that. It's not, there's not 4 there and 2 there. There's just that, you know, there will be different intensities. Okay, for varying, you know, this is just an example, and that's sort of the range that you might get. Okay, anyway, as I said, it's the peak that you need to concentrate on most of all. Okay, so what do we? How do we use this information? Well, obviously there's an angle there, theta, and because this is very, very similar to you know, interference, anything we did with interference, well, there's a single slit there, and we use that for diffraction grating. So we're going to use our equation from diffraction grating. N lambda is equal to d sine theta. But because the angles are so small, okay, sine theta is equal to theta, and that's because all sine theta is a ratio of something, and because it's so small, that ratio doesn't really have much of an effect. Okay, so therefore we just assume sine theta to be theta, and obviously we're only looking at the first order. Okay, because there's only one order. It's not like, you know, there's not spectrums. There's just one order, and that's it. Okay, so it's lambda is equal to d theta. Okay, so what does that mean? Well, obviously lambda is the wavelength. D is the diameter, okay, of the mirror, okay. Yeah, so that's given in your formula sheet, okay. By the way, it's not given in lambda equals d theta. I think it's given as theta equals lambda over d, okay, where d is the diameter of the mirror, you know, in the telescope, and theta is obviously the angle that can be subdued or measured, okay. They use subdued a lot, which essentially just means measured. Okay, so you're just putting in that formula for a given wavelength and diameter. Obviously these are different wavelengths of light, depending on what kind of star or planet it is. That's also equal, so if we put this as theta is equal to lambda over d, we can always say, because we've put x and l here instead of lambda and d, okay, you can have that as being equal to x over L. Okay, well, quite clearly x is our separation and L is the distance to the telescope, or to you, okay, to Earth. Okay, so as I said, that's just another way of looking at this formula. So it's just going off a formula that we already know from way back in AS physics, okay, and just applying it to the situation. Hopefully you kind of see how and why we've done that. Okay, right, so that's kind of it really. Yeah, and obviously you might be asked, you know, to compare these two, simultaneous equation kind of thing, but really it's just being able to understand that these are just two planets and this is just a telescope, okay, and obviously it's just an interference pattern with constructive and destructive interference using, again, as I said, your AS knowledge to create this intensity graph of light. Okay, right, so what we're going to go into now is just a few things called digital cameras, charge coupled devices, which is quite interesting, okay, more interesting than it sounds, and then really go on to ground-based telescopes and interferometry, which is actually another thing that's quite interesting, and then finish off with some different types of measuring, you know, the wavelengths. Okay, so the first thing we're going to talk about is charged couple devices. Well, what the hell is that? Well, basically, in essence, it is of silicon. It's a few thin wafers of silicon divided into individual picture elements called pixels. So what you would see in your TV, obviously, but there's a special type of silicon that they use. Okay, and basically what happens is very similar to the photoelectric effect. Okay, where you have instant photons from the light, which is obviously what they measure. Okay, and obviously they use calculations to determine, you know, what's the energy of the photon, and obviously you can use that to work out, well, how far has it come, what's the distance it's travelled, and use all that out to work the intensity. Okay, and obviously it causes electrons to be removed, and that's how they obviously measure the current and stuff. Okay, and the great advantage of charge coupled devices, I'm not really gonna. I've got a diagram in here, and that's what I'm looking at, trying to debate whether to have a go at drawing it. I mean, I'll probably just confuse you, to be honest. I mean, you can have a look if you can quite see that. My notes there. So I've typed these up. As I said, you could just get that picture offline. Okay, I wasn't really going to draw that, and I'll probably make a complete hash of it anyway. Okay, so as I said, it's just essentially just a thin pixel, okay, which is used because of the incoming photons from the stars, planets, okay, and obviously they use methods of calculating the changing current, okay, to work out any, you know, images, okay, because obviously it removes electrons and then that creates an image, okay, so you don't really need to know how or why that is, but as long as you understand it's to do with the photoelectric effect, you should be absolutely fine. Okay, so charge coupled devices, nothing too difficult with that. The next thing we goes on to talk about, we're going to talk about spectrometers very briefly. Okay, so with spectrometer, well, obviously a spectrometer is just it's a spectrum, and you think, okay, well, that's a spectrum of light. Okay, so it just measures light coming in and analyzes the light. Okay, so I'm only really covering this very briefly because it's not that so it's not that challenging, and there's no diagrams on here, so maybe that's why I've not been special learning this stuff. Anyway, okay, so the next thing you probably might get asked on is ground-based telescopes, okay? And you might get asked on the problems of ground-based telescopes, okay? And one of the main problems is, well, obviously, it's below the atmosphere quite clearly, otherwise that's why it's a ground-based telescope, okay? And any light that is coming into the atmosphere obviously gets distorted, you know, by gas molecules, this, that and the other. And there's various things that distort the signals of light, okay? So if that was on the ground, you would get a different picture if it was, you know, in space. But obviously in space it'd be light to be moving, pulled by gravitation forces. And there's still distortion forces in space, you know, to do with light, okay? But when it gets in the atmosphere, obviously there's a lot more that it has to deal with, so obviously greater scope for error, okay? So obviously that's ground-based telescope, and obviously you could combat that by putting it as high as possible in the places with the least pollution. Okay, and I'm actually going to go on to something called interferometry now, which is quite nice. Okay, so essentially what interferometry is, got it, you know. Hopefully you've copied that table down. So essentially, obviously we've got the world here, and you will have telescopes. Okay, this kind of looks like the moon now, but it doesn't matter. Okay. And all these telescopes link up, okay? Because obviously, one telescope, a single telescope, is very beneficial, okay? You know, you can get a lot of data from it, but the diameter is not that big, especially in comparison to this. Because now we've got the diameter of one, but we're not just adding up the single 4 diameters of, you know, how many diameters of how many telescopes you're using, but the overall range that they cover. Now, granted, obviously, they're not going to cover, you know, certain little bits in the middle and stuff. They're not going to be able to have such a big diameter unless they take over the world. Okay, it's just meant to represent telescopes. But they get a much better picture than a single telescope. Okay, if they work together and share information, you know, obviously they get a better image of wavelengths of light and stuff. So it is very, very beneficial. So that's something called interferometry. It's quite interesting, that. Nearly done now. There's just a few more. Now, I'm not going to go too much into these, but basically you have different types of... obviously, there's different telescopes around the world. They're not all the same. They don't, in terms of, you know, the dishes might be designed slightly differently, okay? In terms of, some might be radio dishes, okay, so sort of a judgeable brand, because I'm obviously from England, so guess that or not. And I only say that because you know, some people watching from Australia, some guy asked if I was American. But anyway, okay, so essentially a radio telescope looks something like this. Okay, so you've got you know, the light or the radio waves will come in even, and it will bounce back up, and then there's kind of a little cone here which is called a subreflector. Okay, and then it bounces back down, goes through the body of sort of this radio telescope, okay, and then it goes through a load of computers and data analytics machines, which obviously project it onto a digital monitor and give information about the radio waves, okay. So that's a very, very crude explanation of a radio telescope, but as I said, probably won't get asked on that, okay. So infrared, so there's various different types of astronomy. There's infrared astronomy, there is ultraviolet and X-ray and gamma. Okay, basically the only difference between the two, obviously you would need slightly different means of telescopes. Ones with greater diameter, for example, that kind of thing. But really, the last few, so sort of, ultraviolet, infrared, X-ray, the main difference is, well, quite clearly, the difference between them is wavelengths, okay? So, if we go back to our formula of lambda equals d times theta, okay, they'll also need a much larger diameter, okay, to be able to measure smaller angles, okay? Yeah, sorry, they will need a much larger diameter to be able to measure much smaller wavelengths of the same angle. So it's just manipulating that formula. Okay? So that's kind of the little bit explanation of the different types of astronomy. But really that covers everything of the first part of astrophysics, okay, so that's all to do with optical and non-optical telescopes, okay, so it's really about reflecting telescopes, the advantages of them, and obviously one of the main things is this maximum central. Oh, actually one more thing I want to mention on this critical before I go. The critical, well, what does it actually mean? Well, it's essentially obviously you can quite clearly say it's just before the two peaks become one, but the more scientific definition for that, or physics or whatever you want to call it, same thing, right? It's when the first peak, okay, goes over the peak of one maximum, okay, one Airy disk goes over the first minimum of the other Airy disk. So basically, it just starts to creep over. The other Airy disks start to merge into one central maximum. Okay, so essentially that is it for this video. So I was going to do a bit of a summary, but it's not that difficult really. We just went over at the start, a bit of GCSE, focal lengths and stuff. Nothing too difficult. And as I said, most of the equations you will be given in your formula sheet, so it's just a case of applying your knowledge really. You probably be asked on the ray diagrams and these kind of diagrams, so if you know them, that's obviously very good. As I said, if you have any questions on the diagrams that I've drawn or maybe the drawings are up to scratch, please do let me know, and I will obviously try and get back to you as soon as I can. Okay, so thanks for watching. Hopefully it's not bored you too much, even though it's been an extremely long video. But as I said, it's covered a third of astrophysics course just in this one video. Well, it probably feels I've covered more than a third of your life. So I do apologise about that, but at the end of the day, it can only be good. Okay, so thanks for watching, and we'll see you in the next video.